continuing 7.2, the from where we kind of left off on graphs yesterday, but I want to do this example. We're dealing with rational functions, we're dealing with fractions, and so one of the things that we use a lot when we're dealing with fractions, or we calculate a lot, is averages. And that's kind of what we're going through here. It's not exactly the way you're used to seeing it, but a 3D printer builds up layers of materials to make a three-dimensional model. Each deposited layer bonds to the layer below it. A company decides to make a small display, small display models of engine components using a 3D printer. The printer costs $1,000. The material for each costs $50. Now, when you get to this point, I'm hoping that right there, you start going, well, that's just a linear function, right? I mean, if I want to write out how much it's going to cost for a certain number of items, the cost would be what function or what equation? Yeah. Y equals mx plus b, but what is m and what is b here? Go ahead.
Okay, it's y equals 50x plus 1,000.
Okay, good. So it'd be 50, and I'm going to use m for model, okay, and plus $1,000 in cost. Okay, not 100, but 1,000. All right. Then it says estimate how many models must be printed for the average. Now, when we're dealing with average means you're adding up everything and dividing by what? How many there are. Okay, so how many are there in this? There's m. So we have to take the cost, because we're doing the average cost, and we have to divide it by m. Okay? So estimate how many models must be printed for the average cost to be 90, or to fall to $90. So when will this average cost, equal 90? That's what we're solving there. Okay? So how many are with me what we've done right there? So really from there, it really is it's just like dealing with any other proportion you've ever dealt with. So if you go back to what you already know, if I was to give you, say, like 5 over x equals 3 over 9, what would you do? Cross multiply and divide. Okay, that times that, that times that. Well, you're doing the same thing here. It's just this proportion, it's 90 over 1, and it's really weird looking. Okay? It's m times 90. And 1 times that, which is that. Okay, and now move the 50 over. Subtract 50 on both sides. And then divide by 40. 1,040ths, or 104ths, or 25. So estimate how many models. We don't even need to estimate. It's an exact value. It's 25. Now I'll tell you, if you actually look through this in the textbook, they tell you to use your graphing calculator, throw it in there, use the trace feature and all that. You shouldn't have to do that. Okay, you could solve that algebraically. What happens to the average cost as more models are printed? Well, what's going to happen to this cost? Yeah. The cost will eventually approach 50. So the average cost will decrease then. Okay? Okay. So you're saying eventually it will decrease to 50. It'll never get below 50. It won't reach 50. Is he correct? Okay, talk about this question right here. Okay, what's happening? So as m gets bigger, what's going to happen to c? So let's go back to our original. That's c. So what's happening to that as this number increases? Try some values out. Matt's saying it's going to approach 50. It's never going to reach 50, but it's approaching 50. Okay? All right, I want you guys to go ahead and talk about it. You only get about a minute on it. Hey, time's up. Yes. Go ahead.
Okay, well, two things actually. One, it's increasing because the next step is multiplying C by M, and so whenever M gets bigger, C also gets bigger because it's multiplied by a bigger number. And two, at some point today, I think we should sing to Emily because it is her birthday.
Okay, we can do that later. Hey, you guys, let's if we were to graph this real quick, where would your horizontal asymptote be? It would be 50. Okay, and we'll talk about how to identify that a little later today. That's part of our lesson. But if we were to graph this on a graphing calculator, our horizontal asymptote would be 50. Okay, so if you have a calculator, go ahead and plug that in real quick, just so we can see the picture of it. Okay, time's up. Hey, first thing, when you put it into your graphing calculator, I want to get done with this problem, so pay attention here. When you put it into your graphing calculator, that's 50 over x plus 1,000. Make sure you put that whole numerator in parentheses. And if you had a bigger denominator, you have to put the whole denominator in parentheses as well. You hit graph. It gives you nothing if you're on the standard viewing window. I am going to go to zoom fit. Now, you may have to figure out which zoom will work best for you. Really, we're only functioning in quadrant 1. If you wanted to, you could do zoom quadrant 1. I'm going to go zoom fit because it actually zooms out and should probably show you the whole picture of it. Okay. Now, from here, I am going to use the trace feature, and I am looking for the horizontal asymptote. So I'm watching my y value. Notice y started really big, and it's decreasing rather quickly. Okay. It's starting to decrease even slower now. What we are looking for is what y is actually approaching here. As x is increasing, which is the number of models, y is still decreasing. Okay, and it's still going down a decent amount. 82, 81. So just kind of keep going with it, right? We keep doing that trace feature. There might be a faster way, but we just keep going. Yeah, mine has this glitch in it. I don't know what's up with that. Anyone else is glitching like that? Hey, it's getting really, it's actually going down slower now. Yeah, we're still going down. It's not like we're not. Okay, it's going down a lot slower now. This is an inefficient way, I just tell you. However, we're doing it. Okay, now it would be really, really nice if there was a much quicker way of doing this. Okay, and there technically is. It's called using algebra. Yeah. All right. The other thing we could do, here's what I'm going to do. I'm going to go to my table now. Oh. My batteries just went dead. Man, that's ridiculous. Unbelievable. Hold on. There are technical difficulties. There we go. Notice on my table. We know I can get... Notice I'm going to change my table set. So I'm going to start at... or I'm going to go up by ones at least. Okay? Go back to my table. It might be easier if I could do it this way and look at what my table's approaching versus using trace. It's a little faster, just so you know. Okay? So as x increases, which is the number of models, what's y doing? It's going down. It's going down until we get to?
Almost 50.
This is ridiculous, dude. This still isn't fast, but it's faster than the other way. Hey, hold on. You know what? Let's go to my table set and let's just say, hey, rather than being 145, let's say it's 1,000. Hold on. We're close to 50. Hold on. Let's go to table set and let's say 1,000,000.
Add more zeros.
All right. What are we getting close to? 50. Now, you guys, hey, Matt was right. It's getting infinitely close to 50. One thing that Sylvia did up here, she changed it to y equals a over x plus k form. All right? So if you take the 50m, or let's put c, so c is y. You take the 50m and divide it by m, plus 1,000 and divide it by m, you get 1,000 over m plus 50. That is your k value. That is the asymptote you're approaching, which would have been much faster than what we did on the calculator. Just so you know. We're going to be doing that today with our equations. Okay, with that being said, let's move on. I want you to go ahead and take a look at your assignment for yesterday. Take that out. We're going to do a couple problems off of that assignment.
Usually I don't like graphing.
Page 2, we're starting out with number 10 here. Please note, yesterday we had our a value was always a constant number. Today our a value is not a constant number. It's x plus 3 on top. And so taking a look at that, I want you to think about what you could do to actually find where our asymptotes are. Okay? You need to know your x asymptote and your y asymptote. Get about 30 seconds. All right, ladies and gentlemen, time is up. Everyone's attention back up here. So, to begin with, what is your x asymptote? Yeah? It's not 0. It's what makes the denominator 0. It's 2. Okay? The x asymptote is 2. All right? So if I'm getting my axis set here, I'm going to go ahead and put at 2 my vertical asymptote. I also know that my vertical asymptote is undefined when x is 2. If I wanted to fill out my table, that'd be x plus 3 divided by x minus 2. I would have 2 plus 3, or 5, divided by 2 minus 2, or 0, which would be undefined. That's why the asymptote is there. Okay? What is the y asymptote? Yeah. 3 divided by x minus 2? Not quite. Yeah? 0? It's not 0. Hey, you guys, so hey, stay with me now. My goal was to get you thinking about it. At least I have done that. Think about your horizontal asymptote is the thing that f of x is approaching. Just like in the previous one, we were trying to figure out, in the problem we started with today, we're trying to figure out what our cost was approaching when the number of models increased infinitely. Right? So when we put in 1,000,000 models, it approached 50 on that previous problem. How many remember that problem? Okay, that's why we did that. So this problem right here, we're trying to figure out what this fraction is approaching. Ignore that it's an ugly fraction. We're trying to figure out what that fraction is approaching as you increase x. Okay? That's what the horizontal asymptote is doing. Okay, so let's even simplify it even more. We are trying to figure out what y is approaching as our fraction gets bigger, or our value of x gets bigger in our fraction. So currently we have x over x, we also have a little extra stuff on the top. Okay, why do I say it's a little extra stuff? I'm going to make 3 really small and 2 really small. Why do I say that? Because x is about to get really big. So like if I say, if I'm using big values of x, if I'm plugging in big numbers, like I say, hey, 1 billion. Okay? So if I have $1 billion, let's go in dollars. If I have $1 billion and you come up and say, hey, Mccoy, can I borrow 3? Yeah, chump change. There you go. There you go. All right. I'm not even worried about it. Okay? May have to charge you interest, yeah. Okay, but hey, it's $3 in relation to $1 billion. So this 3 is really, really, really trivial. Stay with me here. This is a trivial amount, as is the 2. Correct? How many are with me right now? So really what you have is 1x divided by 1x. Well, that could be 1 billion, 1 trillion, 1 zillion, 1 whatever. You have a huge amount, one of a huge amount, divided by one of that same huge amount. What is this? That is 1. Your asymptote is 1. Okay? How do we do that? We are saying if I ignore the trivial small chunks, remember the 3 and the 2 are small. They're not reliant on x. That means there's not an x attached to them. They don't mean anything in relation to us finding the asymptote because this number is so big. Okay. It's be the same thing. If it was like negative 1 million, it would mean the same thing. Okay? Yes?
So if it was like 2x plus 3 over x minus 2, would it be that? Would the asymptote be 2?
Yes. Okay, so what you're doing, yeah, you're looking at the numbers in front. You're looking at those leading coefficients. 1 divided by 1 is 1.
Is that true with all equations where it's x? Like, for example, number 11, that's x minus 5 plus, or over x plus 3, is that 1 as well? Is it just like that for all of them?
Yeah, so, yeah, 1 over 1. Yeah, same thing. Yeah.
So graphically, what does that number on top do? The minus 5?
We can show that here in a while. Okay? Hey, you guys, let's take a, well, let's first do this. What our y asymptote here is 1. Okay? I want you to go to number 11. We're obviously not done with 10, but go to 11. List your x and y asymptotes. Okay, what's x?
Negative 3.
Negative 3. It's what makes this 0. What's y?
1.
Okay? It's 1 divided by 1. All right? Go to number 12. List your x and y asymptotes. Okay, x is 2x minus 6 equals 0, the bottom. What's that?
3.
X equals 3. Y is? Yeah, it's 1 divided by 2. Now, for those of you that are confused there, remember, and I keep saying it's as, I've been saying it's as y, or excuse me, as x gets really big. It also could be when x is really small, but it does the same thing. It approaches the same line. It's as x approaches infinity or negative infinity. What is y doing? Okay, well, the same thing happens here. You really have, on number 12, you have 1x plus 4 and 2x minus 6. Once again, when these numbers get really big or small, these don't really matter. Okay? That is 1 million divided by 2 million, which is 1/2. Or negative 1 million divided by negative 2 million, which is 1/2. So our y asymptote is 1/2. Now please note that all the problems we've done so far have the exact same powers. That's x to the first and x to the first. It changes when this becomes like a squared up here and a first power down here, or a squared down here and a first power up there. That will be later. We will deal with that. Okay? Okay, so going back to our tables now. On this one, I have my well, actually, let's put in our y asymptote. It would be really nice if our equation was in a form that like we graphed yesterday. Okay, and I know on the previous problem we said, well, if you had we could just divide by the denominator, or the denominator, but we didn't have a linear, we didn't have two terms in the denominator. We only had one. So here, if we are going to actually, if we wanted to change it in this form, okay, and actually a over x minus h plus k, if we wanted to go to that format, really what you need to do is use that handy skill of polynomial long division. Okay? So that's where you would say, well, I know that if I have x minus 2 and I'm dividing x plus 3 by x minus 2, how many x's go into x? 1. 1 times x is x. 1 times negative 2 is, and I subtract, which means the same thing as adding the opposites. So that becomes negative and that becomes positive. So I get a remainder of 5. Okay? That's 5 over x minus 2. Thanks. All right. Everyone see the h and k? Okay, let's rearrange it. It's y equals okay, how many of you can see the h value? Right here, right? K value, the thing that where we saw the asymptote, it's 1. I mean, you could have done that to begin with. I just wanted to make sure that you could look at that and find the horizontal asymptote. But that's, hey, there you go. That is this format. How is that helpful? Well, it tells us, remember yesterday we said that a term, that's how much you're away from each asymptote. You go over 1 from where the asymptotes intersect, over 1 and up. There you go. Up 1 and you're over 5. Same thing here. Over 1. Down 5. Glad I could help. Okay? You may want to pick a value in between and find out where that bends. Otherwise, some of you just connect the points, and that's not a good thing. So maybe you throw in like 1, 2, 3, 4. Okay? Or it was brought up yesterday. If you wanted to just more focus on, let me write this format here. If you want to ignore that 1 that's shifting up, you could do that. But some of you, if you just pick, let's say 1, 2, 3, 4, put 4 in. 4 minus 2 is 2. That's 5 halves. 5 halves plus 1. 3.5, yeah. Okay, and it curves. There, we've got it. You can do the same thing. You can put 0 in. When x is 0, that's negative 2. That's negative 5 halves plus 1 is negative 1.5. All right. I think you got it. Okay, that's what you're doing there. You guys, Sylvia had one question just I want to address up here, and if you memorize this stuff, fantastic. If you don't, it's up to you. Okay? When you're in this format, this is just a little extra info. Please note there's not a constant value out here right now other than 1. So if you're in this format, the x-intercept is equal to a. The y-intercept is equal to a over b. Your asymptote is equal to, well, I guess you have two asymptotes. X equals b. Y equals, what would it be? It's not a. What's your asymptote on this right here? 1. In this format, those things are true. Now, with that being said, you're not going to, sometimes you'll be in that format, but you're not always in it. If you really, really want to do these in a way that you can remember everything, I would put everything in the format of, and I'll put this back up here in a minute, I put everything back into this format that I could. And use polynomial long division to do that. Okay? All right.